Okay, so today we're still, of course, in circles, but we'll be looking at segments of chords, tangents, and secants. Of course, if the chords intersect, you've seen the diagram exactly what happens, and each of those chords is broken into two segments. And this is the math that we can do with that. So for like chord AB, I know the segment from AE times the segment from EB will have the same value if we do that to the other chord, right? So that chord CD, if we break it up into EC and ED and multiply those two pieces together, it has to be equal to each other. Again, these often make much more sense to me when we see it with numbers. So, okay, chords intersect each other. So I know the distance from N to K multiplied by the distance from N to J has to equal the distance from N to L times the distance from N to M. Of course, distance from N to K is just X. Distance from N to J is X plus 4. The distance from N to L is X plus 1. The distance from N to M is X plus 2. Distributive property was used on the left-hand side. And then on the right-hand side, FOIL was used. I'll do an example later on this presentation that actually shows that step-by-step work with the FOIL there. Now, this time we get real lucky. If we subtract x squared from each side of the equation, there are no more x squareds. And we're like, oh, we won't have to worry about factoring. We can just solve. 3x is subtracted from each side. We've got an answer of 2. Uh-oh, look at the directions. Were we asked to find x? Nope. We're asked to find the length of the chords. So the distance from M to L will be x plus 2 plus x plus 1. Substitute the number 2 in every time we see an x. Distance from J to K. Substitute the number 2 every time you see an x. And now we have found the distances. Again, remember, go ahead and pause the presentation if I'm going too fast. Replay it if you need to replay it. Okay, now first some vocabulary here. Now the tangent, all of it is outside the circle, but with a secant, because it intersects the circle twice, part of the secant is inside the circle and part of it is outside the circle. Of course, the tangent segment is just a part of a tangent line. And a secant segment is just a part of a secant line. Notice to be a secant segment, one endpoint has to be on the outside of the circle. And for the outside part of the circle on that secant, we call that the external segment. So the entire segment is called the secant segment, but the part outside the circle, the external segment. Notice we don't say that for the tangent segment because the entire tangent segment has to be outside the circle. Okay, now what if we have two secants? All right, so EA times EB is equal to EC times ED. All right, in each case, we're taking the external segment of the secant, multiplying it by the entire segment of the secant. Again, this also makes more sense to me when I see with numbers. Of course, RP is 9. From R to Q, it's 9 plus 11. RS, of course, is just 10. But from R to T, I've got to take the 10 and add it to the X. Notice it doesn't matter which way I do the adding. I can do 11 plus 9 or 9 plus 11. Or I could have done 10 plus X instead of X plus 10. Right, it's also the external segment multiplied by the entire segment. So we simplify, subtract 100, divide by 10, we get an answer. Again, later on this PowerPoint, I'll go through an example slower in greater detail. Now, what if one of them is a secant, but the other one is a tangent? Now, at first glance, you think, hey, we're doing something different than we did before. We're actually not, because if you think about the tangent, the part outside the circle is E to A. The entire segment is E to A. So we're still kind of multiplying the outside part times the entire thing, because we're doing EA times EA. So, of course, it just becomes EA squared. For the secant, it's still the external segment, EC, times the entire segment, ED. So the distance RQ has to be squared. And then we have to do RS times RT. The distance RQ, of course, is 16. RS is the external segment of the secant, so that's just X. RT is the entire secant segment, so that's the X plus 8. Uh-oh, we could not get rid of the X squared, so we'd try to factor. Can I think of two numbers that multiply to be negative 256 but add up to 8? Nothing comes to mind, so if you can't think of something, go to the quadratic formula. And in this case, it turns out that there's no way we could have factored, because look, we're stuck with the square root of 17. Right? Anytime you use the quadratic formula and you get stuck with the square root and you cannot simplify that square root, that lets you know you never could have factored. Uh-oh, this is geometry. We only want positive numbers for distances. right, -4 subtract 4 root 17 would be a negative number. Can't use that for distance. All right, distance cannot be negative. The shortest possible distance, of course, would be 0. So normally we have a positive number. Of course, if there's no distance between them, then we'd actually have 0. So now we actually know the distance from RS is about 12.49. Okay, so now let's do some examples where I actually show every step-by-step detail en route to the solution. The chords intersect. So I know 6 times x has to equal 3 times 4. 3 times 4, of course, is 12. I'm going to divide both sides by 6. X is 2. Okay, so on the one chord, it's broken into x minus 10 on one side, x plus 12 on the other. The other chord is broken into 2 pieces, x on one side, x minus 6 on the other. Now I have to use FOIL, or if you know a different method that you prefer, I like the FOIL, first, outer, inner, last. Some students like to draw the arrows. Some students like to put the letters FOIL. Other students don't need those visual aids, whatever works best for you. And of course, on the right-hand side of the equation, I'm going to use the distributive property. Well, let's combine like terms. It looks like O and I will combine on that left-hand side. The 12x and the negative 10x can combine. So now I've got x squared plus 2x minus 120 equals x squared minus 6x. We're going to get real lucky because if I subtract x squared from each side, the x squareds are going to cancel out. They'll be gone. So I'm not going to have to worry about factoring. I'm not going to have to worry about using the quadratic formula. Got really lucky here. Now, to get all the numbers with the x's on one side and everything without an x on the other, the easiest way is actually just subtract 2x from each side. That way, in just one step, I have every term with the variable x on one side, every term without the number x on the other side. Of course, I don't want negative 8 times x, I just want x. So the opposite of multiplying by negative 8 will be dividing by negative 8. And so there I have some very nice step-by-step work. And I came up with an answer of x equals 15. Again, pause the presentation whenever you need to. Replay parts of the presentation whenever you need to. Okay, here comes some fun. We got the secants. Of course, on one of the secants, the external segment is just 6, but the entire segment is 4 plus 6. On the other secant, the external segment is 5, but the entire length of that segment is x plus 5. Well, I can simplify the 4 plus 6 to get 10. Of course, 6 times 10 is 60. I use the distributive property on the right-hand side. Okay, the 25 does not have an x with it, so let's subtract 25 from each side. Now every term with an x is on one side, every term without an x is on the other. Of course, I don't want the value of 5x, So let's divide by 5. And we find that x has a value of 7. Okay, now I've got an external segment of length 21, but then the entire segment is the 2x plus 8 plus the 21. The other secant, external segment is 27, the entire length, x plus 27. Looks like I better add that 8 and that 21. That'll get 29. Looks like I need to use the distributive property to multiply out. Of course, 21 times 29, I'm going to grab a calculator. All right, it's possible to show step-by-step work and also have to use a calculator. Same thing with 27 times 27. Most of us don't have that memorized. Yes, it's a perfect square, but most of us don't memorize our perfect squares up into the 20s. Uh-oh, got x's on both sides of the equal sign. So I'm going to subtract 27x from each side. Good news, everything with an x is on the left-hand side. Bad news, that 609 does not have an x. Let's subtract 609 from each side. I don't want 15 times x, I just want x. So to undo the multiplication, I will divide. And I come up with x equals 8. Again, as much as possible, I try to keep my equal sign falling straight down the page. Secant and a tangent. Well, the external part of the secant is just 5. The entire secant is x plus 5. And that equals to 10 because we just square the value of the tangent. If you want to try to treat the tangent like a secant, the external part of the secant is just 10. The entire tangent is just 10. Of course, 10 times 10 is 10 squared. Of course, distributive property. Ten times 10, of course, is 100. Looks like we'll subtract 25. And then the opposite of multiplying by 5 will be dividing by 5. Okay. External part of the secant is 9. The entire secant is the 7 plus the 9. Because the other one is a tangent, we'll just do x squared. Now here comes the exciting part. I've got to take the square root. Now in algebra, I know when I take the square root and a variable is involved, I need to put the plus or minus in front of that square root symbol. Right? So in algebra, I should be trained to understand that x could be 12 or that x could be negative 12. Uh-oh. Geometry. All right, we've got some definitions. And one of the definitions is that we will not use a negative number for distance. So we will only use x equals 12. If you're wondering why we did not do an example where they're both tangents, remember in a previous lesson we dealt with that. If they're both tangents, they're equal in length. Notice the IXL is a throwback from when we were doing the inscribed polygons. There will be one more PowerPoint presentation tomorrow, but it's going to be a review.